Hello, my name is Sandra Baumgartner, and today I'm going to talk about visual pattern recognition with on-chip learning. I did this work together with Alfa Renner, Rafaela Kreiser, Dongchen Liang, Giacomo Indiveri, and Julia Sandemirskaya. Today, in object recognition for robotic applications, there are a few specific challenges, such as that patterns need to be learned quickly, and ideally, a model can be updated continually whenever new objects appear. Furthermore, pose invariant recognition and pose estimation are also of great importance. To address these challenges, we present the spiking neural network architectures, which enables few-shot, unsupervised online learning with autonomous selection between learning and recognition, while also estimating the location and the scale of the presented pattern. We validated our architecture on Intel's neuromorphic research chip Luigi, directly interfaced to an event-based camera. We use an event-based camera which achieves low latency and low power consumption while having a high dynamic range. Pixel asynchronously emits spikes whenever their illuminance changes, which means that patterns have to be jiggled by hand in front of the DBS. Luigi, the neuromorphic chip we use, allows us to implement our SNN on a hardware level by providing more than 100,000 single neuronal units per chip, which can then be connected via synapse. On Luigi, networks are trained using local spike timing dependent learning rules. The SNN architecture we've developed consists of a 4-layer feed-forward network and an arbitration mechanism which coordinates the self-supervised learning. Now I will go through the different parts of the network. Firstly, the downsampled output of the DBS is processed using a simple convolutional layer which kernels responding to horizontal and vertical bars. Then the feature map goes through either the learning or the recognition pathway. Which of the two is decided by the arbitration mechanism, which will I explain later. In the learning pathway, in green here, different possible scalings and locations are hardwired into the network, so that all of them can be learned even though we present only one of them. In the recognition pathway, here in red, the wiring is done in a way such that only the correct scaling and location causes spikes in the output neuron group corresponding to the correct pattern. The learning then takes place in the plastic synapses connecting the mapping neurons to the output neurons. Initially, all plastic synapses have a weight of 0. When learning is triggered, the output neurons of the first output group get stimulated by the arbitration mechanism. This will cause them to spike. The learning rule we use will then change the synaptic weight of each synapse connecting a mapping neuron to the stimulated output neuron using Hebbian learning. With the learning rule we use, we get an excitatory synapse when the presynaptic mapping neuron has a high firing rate, and an inhibitory synapse when the firing rate of the mapping neuron is low. And to conclude the discussion of the mechanism, let's talk about the arbitration mechanism. It is basically a neural state machine that receives input from the feature neurons and the so-called motor neurons, which are active whenever the DBS is moved around. This input is then used to control which pathway should be switched on and which output neuron group should be stimulated for learning. It triggers learning if the following conditions are all satisfied. First, no output must be active, indicating that no pattern is recognized. Secondly, we need to have sufficient activity of the feature neurons, which indicates that there is indeed a presented pattern at the input that can be learned. Thirdly, the DBS must not be moved around too much, for otherwise the pattern is not stable at the input. Due to the simplicity of our convolutional layer, we just used 4 different patterns for evaluation. Our results show that the network is very robust against noisy inputs from the DBS. This is mostly because a lot of noise already gets filtered by the features in the convolutional layer. Therefore, we also evaluated how much noise we can inject directly to the neurons of our network. We thus injected noise to the feature neurons. Here we could also inject up to 20% of noise before the classification accuracy began to drop. This result will become relevant as soon as the network is implemented on mixed signal neuromorphic devices which might suffer from inherent noise. As you can see here, in addition to the classification, the scale and the location of the presented pattern were also estimated by firing rate of the output neurons. We presented a spiking neural network architecture for object recognition in robotics with the following key properties: fast detection and online self-supervised learning of newly presented patterns. The SNN size scales linearly with the number of objects it is able to store. Scale and position estimation of a presented object by autonomously arbitrating between learning and recognition. Finally, we implemented and tested our network on Luigi and evaluated its robustness in terms of possible inherent hardware mismatches as they might appear on mixed signals in neuromorphic devices. Finally, I'd like to thank our institutions and funding agencies for making this project possible. Thank you.